Right, so hey everybody, good morning. My name is Javier Sagasti-Brena, and I will be presenting this recent work we released on Archive, a preprint titled Two Routes to Scalable Credit Assignment Without Weight Symmetry. This is work that has come out of the Stanford Neuroscience and Artificial Intelligence Laboratory, which I have been working on with amazing contributors, Aran Ayebe and Daniel Kunian as well, who are also in the room. So let me just briefly go over the agenda for today. I'll start with some motivation for the problem that we're tackling and just highlight some problems that normally arise when dealing with backpropagation algorithm. I'll focus on one of those problems, particularly on weight symmetry, and then go over some previous proposals that have attempted to break weight symmetry and to get this to scale at different tasks. I will then go into the regularization-inspired learning rule framework that we formulated, along with some evaluation criteria for different learning rules that we're able to formulate with this framework. I'll then segue into some results, segmenting between local learning rules and non-local learning rules. And finally, I'll just add some concluding remarks. So without further ado, let's just get started. Backpropagation is the workhorse of modern deep learning, and it's the only known learning algorithm that allows multi-layer networks to train on large-scale tasks. However, the neural plausibility of backpropagation has long been disputed for its use of an error signal, continuous derivatives of the activation functions, alternating forward and backward passes, and maybe most famously for its use of the transpose of the forward weights in the backward pass, assuming different neural circuits implement the forward and backward path. The focus of this work will be precisely this last piece, the requirement that backpropagation requires weight symmetry in the forward and backward paths. Let me just clarify exactly what we mean by these. Consider backpropagation on a particular layer of an artificial neural network under the previous assumption of independent forward and backward paths. The top of the figure shows the activations of each layer as blue circles, as well as the weight matrix WL with the synaptic connections of between layers. Activation functions and biases are omitted in this diagram. But then further upstream, the output of the network is going to be compared against the target, and an error signal is computed and then it's going to be sent back through a different path. The bottom section of the diagram shows the backward path transmitting the exact gradients through the network. A particular gradient, for example, say gradient L+1 in a red circle, will be used to update WL and will then be sent backwards upstream through the network with a particular set of synaptic connections imposed by WL transpose. So then, this is the backpropagation framework, and here we can see the weight symmetry problem. So now, under this framework, we can break the weight symmetry constraint by substituting the transpose of the forward weights by a different weight matrix BL. The error signal computed at the end of the network will be the same, but once it is propagated backwards through the network, it is no longer an exact gradient of the loss function with respect to the forward weights, since it involves transformation by different weight matrices. We call it instead a pseudo gradient, but importantly, this can still be used to update the forward weights. The question that arises now is how should the updates to backward weights be conducted? That is, what should the dynamics on these backward weights be? Now let's look at some previous approaches to introducing dynamics on the backward weights. Here we'll only mention 3 of them. For instance, Lillicrop et al. In the 2016 Nature paper, they showed that by imposing no dynamics on B, rather by keeping it fixed to initial random values, shallow networks could learn to perform reasonably well on categorization tasks. However, this approach did not scale really well to neural networks, to deeper neural networks. The update then was just really imposing no dynamics on B. The weight mirror update, which is presented in a more recent work by Akruta et al., assumes that the feed-forward activations are going to discharge noisily into the backward path, and then a Hebbian update is computed based on the noise. You can see the update to be there. Lastly, the Cohen-Pollack algorithm proposes mirroring the update to the forward weights and is also adding weight decay. So these are several proposals for biologically plausible learning. So how can we think about them in a unified setting? An idea would be to try to think of the backward weight updates as stemming from the derivative of a loss function. If such a thing were possible, this would crucially allow for very simple and flexible integration with the current deep learning stack. In this work, we will formulate a regularization-inspired learning rule framework, which encompasses existing approaches and also elucidates novel learning rules. We consider a global loss L, which we can optimize as a function of the forward weights and the backward weights. The forward weights parameterize the global cost function J. The backward weights specify a descent direction. And the regularization R constrains the relationship between the forward and the backward weights. Every step of training consists of two updates, one for the forward weights and one for the backward weights. The forward weights are updated according to the error signal on J, propagated through the network by the backward weights, as previously discussed. The backward weights are updated according to the gradient descent on R. Thus, R is responsible for introducing dynamics on the backward weights, which in turn impact the dynamics of the forward weights. The functional form of R gives rise to different learning rules, and in particular, the locality of a given learning rule depends solely on the locality of the computations involved in R. To build a regularization function R, we consider a set of primitives defined in the following table. To classify the primitives, we use the criteria for locality described by Whittington et al. In their 2017 paper. By looking at the gradient of the primitives with respect to the backward weights, we can tell what the update will be, and we can easily categorize the primitives as local or non-local according to the previously defined criteria. These simple primitives can be linearly combined to define different learning rules by defining their respective regularization functions. It is easy to see how feedback alignment falls under this framework, as it would mean to simply make the regularization term and the loss identically zero. Weight mirror, on the other hand, can simply be viewed as a linear combination of the amp and decay primitives with appropriately chosen coefficients. If we look at what the derivative of RWM with respect to the backward weights is, we obtain the previously defined update rule for weight mirror. This encompasses some previous proposals. Further, a variety of novel learning rules can be derived by parametrically combining the primitives. We'll go into detail a bit later, but these are all novel learning rules. Now let's go into evaluating the learning rules. There are two main metrics by which we propose to evaluate them. We'll first look at task performance, given that in order to survive, any given animal must perform well at a relevant difficult behavior. This is also in line with the point that Barton et al. Highlighted in the 2018 paper, where they mentioned that alternative proposals to backpropagation perform well on constrained problems with smaller networks, but they fail to perform well at scale with deeper architectures on more complex tasks. Thus, we consider ImageNet top 1 validation accuracy since performance optimized CNNs provide the most effective model of neural responses to the primate ventral visual stream. We'll also extend Bartonov's proposal and look at learning rules metaparameters robustness. It is commonly the case that networks trained with backpropagation show good transferability of hyperparameters tuned on smaller scale versions of the network to deeper architectures. That is, hyperparameters that seem to work well on shallower networks also work once the network becomes deeper and require minimal adjustments. Thus, we will be looking at ImageNet top 1 performance across different models for a fixed set of hyperparameters. We'll now begin an exploration of local learning rules by trying to reproduce the published weight mirror result. We find the result to be quite sensitive to metaparameter choices, and our obtained performance falls quite below the reported WM performance. Thus, we will attempt to tune the metaparameters by running a large-scale search using the tree of Parsons estimators algorithm. Even then, using the same metaparameters that we optimized for on ArrestNet 18 and use them to train at deeper models fails completely in both the baseline and the search. Whereas when we do the same for backpropagation, we can see in the plot that there's a monotonically increasing performance as a function of model depth. By analyzing the sources of instability in the weight dynamics of weight mirror, we introduced two strategies to further stabilize them. First, we wonder whether this could be helped by means of using an adaptive optimizer on R instead of the prescribed vanilla gradient descent optimizer. We ran an additional search to retune the hyperparameters for this use case and found that the learning rule presented improved metaparameter robustness. So the second approach we followed included adding stabilizing layer-wise normalizing operations in the architecture in the favor of batch norm and layer norm, and we found further improvement, as we can see in the green line. Further analysis indicated that by adding an additional primitive to the weight mirror R function, we could increase the metaparameter robustness. The resulting novel learning rule, called information alignment, is inspired in penalizing a layer-wise autoencoder loss and has some desirable properties to normalize the updates. So the first of our proposed routes to improve credit assignment without weight symmetry is to improve the stability and metaparameter robustness of these local learning rules. Now let's go back to non-local learning rules and consider again the problem of stabilizing weight mirror. What if instead of adding new primitives, as is done in information alignment, we replace the existing primitive. Symmetric alignment is defined by replacing the amp primitive with a non-local self primitive, which adds to a regularization function proportional to the Euclidean distance between the forward and backward weights. Symmetric alignment matches backpropagation in performance, as can be seen in the plot, and robustness as well, without any metaparameter tuning or specialized learning schedules. Activation alignment, on the other hand, is defined by replacing the decay primitive with a non-local sparse primitive, which leads to a regularization function proportional to the Euclidean distance between the forward and the backward activations. Activation alignment also matches backpropagation in performance and robustness. While these non-local strategies don't suffer the stability issues of their local counterparts, they are non-local and thus can be made subject to similar scrutiny as backpropagation. However, recent work has shown how noisy perturbations in the presence of spiking discontinuities could provide neural mechanisms for these methods. To test the scalability of these mechanisms, we model their uncertainty by adding Gaussian noise to the backward updates during learning. Crucially, both symmetric and activation alignment are more robust than backpropagation to these noisy updates. So the second of our proposed routes is the further characterization of biological mechanisms for these non-local learning rules. So let me just start the conclusion by saying, just summarizing what we've gone through. In this work, we presented a unifying framework that allows for the systematic identification of robust and scalable alternatives to backpropagation. We obtained through large-scale searches a local learning rule that transfers more robustly across architectures than previous local alternatives. Nonetheless, our performance and robustness gap persists with backpropagation. We also formulate non-local learning rules that achieve competitive performance with backpropagation, requiring almost no metaparameter tuning, and that are robust to noisy updates. Taken together, our findings suggest that there are two routes towards the discovery of robust, scalable, and neurally plausible credit assignment without weight symmetry. The first route involves improving local rules. To aid in this exploration going forward, we have written an open source TensorFlow library, allowing others to train arbitrary neural networks and learning rules at scale, distributed across multiple GPU or TPU workers. The second route involves further refinement and characterization of scalable biological implementation of weight estimation mechanisms like symmetric or activation alignment. We invite you to take a look at our preprint for more details, and we thank you for your time, and I'd be happy to take some questions now.